Good afternoon, folks. Good afternoon, folks. Welcome. I'm going to turn this up a little bit, which will probably start blasting when Andy starts speaking. I want to introduce today's speaker, who is our own Professor Andy Lucas. Andy was an undergrad at Stanford, graduating in 2012 before earning his PhD in physics from Harvard in 2016 with advisor Subir Sachdev. He went back to Stanford for a few years as a postdoc and then joined the CU physics faculty in 2019. Andy has been awarded both an NSF Career Award and a Sloan Foundation Fellowship since he arrived at CU. And he has published and given invited talks all over the world on topics ranging from superfluid turbulence and vortex dynamics to electron hydrodynamics to quantum information issues and many other topics, too numerous to list here. We're honored to have him here today giving our first colloquium of the year on speed limits and locality and many-body quantum dynamics. So please join me in welcoming Andy Lucas.
Okay. Yeah, let me know if the mic is either too loud or not loud enough. Yeah, it's my pleasure to be talking today. Is it?
I think it's too quiet.
It is on. Okay, is that better? Okay. All right, I'll assume it's fine. Yeah, so I'm happy to be speaking today. Today I'm going to talk about some work that I've done over the past 5 years or so with many of my current and former group members. So in the top row, I have current sort of postdocs and students in my group. Qifeng Chen is a former undergrad of mine, now a PhD student at Caltech. And then Min and Alexei were sort of at Maryland when I was working with them. So there's also a review article that I wrote with Chao and Qifeng that showed up in March. So I put friendly in quotes because there are theorems and proofs. This is mathematical physics. But I think this is about as friendly of an introduction to the subject as you're going to find. So if you're interested in what I'm talking about today, there are many details and extensions you can read about here. OK, so to give you kind of a brief outline for today's talk, I'll motivate the problem of emergent locality and then describe the sort of canonical version of a theorem on emergent locality in many-body systems due to Lieb and Robinson. I'll then spend some time describing some applications of locality bounds in physics, ranging from things that maybe aren't so surprising to some examples that I think are rather shocking, at least at first glance. So I hope to convince you that these notions of emergent locality are actually very powerful and give us quite a lot of constraints on many-body physics and on what's possible in many-body systems. At the end of the talk, I'll discuss some of our work on extending Lieb-Robinson bounds to more realistic settings and more generalized settings, and that's it. OK. So the first time in physics that we come across a notion of a speed limit, in particular a speed limit on information, is in special relativity. In special relativity, we know that information cannot travel faster than the speed of light. And the reason is very simple. We know from the Lorentz transformations that if I have here 3 events in space-time, A, B, and C, in one inertial frame, if A and B are time-like separated, and B occurs after A, while C and A are space-like separated and C occurs after A, I can find another reference frame where C occurs before A, while B, of course, still must occur after A. If I could send information faster than the speed of light, then in inertial frame 2, A would have caused C, but C occurs before A. And that opens up a whole can of worms of science fiction that we don't want to do. So we say that information must travel no faster than light, and A can only influence B. Now, you might ask, just as a sort of fun aside, the speed of light is a big number. It's 3 times 10 to the 8 meters per second, more or less. So do you actually ever notice this in your everyday life? And OK, in my generation, the context where you would notice the finite speed of light is if you tried a game with someone in Australia and there's lag. OK? You cannot send signals there and back faster than about 90 milliseconds. And your internet service provider, as horrible as I'm sure it is, comes within a factor of 10 of saturating this fundamental limit on information speed. So I think this is kind of remarkable because there's all kinds of fiber optic cables and networks and so on. And still, in our classical world, we come very close to saturating Einstein's limit on how quickly we can send signals. But this talk is not about relativity. This talk is about emergent speed limits that arise in non-relativistic systems. And the simplest example of this is the emergence of sound waves in fluids. If you're listening to what I'm saying and not just looking at the screen, then information is being transmitted to you via sound waves, which travel 10 to the minus 6 at 10 to the minus 6 C. Okay? And in this talk, we'll be describing how in quantum systems there are also emergent speed limits, very much like the speed of sound, that are parametrically smaller than the speed of light and which constrain the propagation of information in systems ranging from spin models of magnetism to quantum computers. Okay. All right. So let's begin with a sort of simple warm-up for how a non-relativistic system can have an emergent notion of locality and a finite speed limit emerge. If we start with just a model of one particle hopping on a one-dimensional lattice, right? So I'm imagining my particle here doesn't move in the continuum, but maybe it's sort of mostly localized around atoms in a crystal at sites 0, 1, 2, and so on. We often sort of simplify such models in physics to a kind of tight binding-like description, and we assume that maybe an electron moving through a crystal just hops from one site to the next. The Hamiltonian that describes that motion in quantum mechanics will look like this. And at least when I taught quantum mechanics, this is a sort of undergrad exercise to find the energy levels and eigenfunctions of this Hamiltonian, and they look like this. So we have eigenstate plane waves, but of more interest to us here will be the eigenstate, or the eigenvalues, rather, given by this formula. Now, if we think about how we might send information with this single particle, what we might do is encode some information in the shape of a wave packet, or even just the existence of a particle at maybe the origin. And then we would ask, how long does it take to see that wave packet arrive some distance r away? The time it takes for the wave packet to be transmitted a distance r will be bounded because there's a maximal group velocity associated with this dispersion relation. And we know from sort of elementary wave mechanics that when we have this kind of complicated dispersion relation, information propagates sort of with the overall envelope of the wave packet at the group velocity. And in this problem, the group velocity becomes bounded by basically the exchange interaction J times the lattice spacing divided by Planck's constant. Okay? And although this is a single particle problem, this is kind of the schematic scaling for emergent speed limits in general quantum mechanical systems. And in solid state, this emergent velocity will typically be about 2 to 4 orders of magnitude smaller than the speed of light. This is kind of the scale of the Fermi velocity in a metal. Okay. So here's a notion of emergent speed limit. But this is a single particle problem. And this talk is really about many-body physics. So rather than talking about a single particle that hops from one lattice site to the next, we really have in mind models where we put maybe a spin 1/2 degree of freedom on every site, or because this is the 21st century, we talk about qubits that can be 0 or 1, and we just write x, y, and z instead of the Pauli matrices sigma x, y, and z. Okay. Now, there are some important differences between the single particle and the many particle problem. Maybe the most mundane difference, although we'll see that it actually is somewhat conceptually important, is that the structure of the Hilbert space has completely changed. Okay? In this problem, even if we just have a single qubit on every lattice site, the Hilbert space is uncountably large. Okay? So this is like a real infinity in mathematics. Instead of just saying we have a particle that's on this lattice site or this lattice site, now we have to specify the state of the system by specifying the state of every qubit on every lattice site. Okay? This is important because it means that even under sort of what might seem like very minor and simple small rotations of the wave function, we can actually kind of completely orthogonalize a quantum state very efficiently in our high-dimensional Hilbert space. So the way we thought about locality for the single body problem, by thinking about sort of how a wave function evolves in Hilbert space, we'll see doesn't work. Okay? As a simple illustration of this, let's imagine that I start off with a bunch of qubits in state 0, and then I rotate these qubits, each of them by a small angle delta, so that they're in a superposition of the state 0 and 1. Now, if I was just talking about a single qubit wave function, okay, the screen up here went blank, but it looks fine. Okay. If I was talking about a single qubit wave function, these two states would basically be the same thing. However, when I have n of these qubits, these two wave functions become almost orthogonal. Okay? So the overlap of these states is exponentially small in n, no matter how small delta is. Okay? And this tells us that there's really no spatial locality in many-body Hilbert space. Okay? And indeed, you can think about the structure of our Hilbert space as a kind of hypercube, which is an extremely high-dimensional object. There are n of these axes, right, if I have n qubits. And if I want to think about wave functions evolving in this space, I have a quantum mechanical wave function sort of quantum walking around this hypercube. There's no notion of nice locality the way that our single particle hopping along the lattice had. Okay? So therefore, we need sort of a better way of thinking about locality. And the way to think about locality in a many-body system will be not to think about states, but to instead talk about operators. There's a physical reason for this. Okay, maybe in 20 years, we'll be doing experiments on sort of honest many-body states. But at least today, it's fair to say that we do experiments by looking at correlation functions of sort of few-body observables. So we don't really probe the many-body state itself, but rather simple kinds of correlation functions. So the kind of experiment we should expect to do to probe any emergent notion of locality in physics would go something like this. I prepare a state psi, and then maybe I do an experiment twice. The first time, I just take the state psi, and I evolve it for some time t with my Hamiltonian. And I guess at this point, I'm setting h bar to 1. That will continue henceforth. OK. After I do that, I get some state phi. And then I repeat the experiment again. But before I evolve in time, I just apply a small perturbation on one lattice site. You can think of this as like a small rotation on the qubit at site 0. Okay? And this epsilon is just sort of for pedagogical purposes. Okay? All right. Now, the question that I want to ask is, if I look at local correlation functions of an operator some distance r away at some later time t, does that operator, is the expectation value of that operator care about the perturbation that I've applied or not? Okay. So there's a few lines of calculation that you can do, but I've displayed it here, but in a nutshell, we can ask how different is the expectation value of an operator some distance r away, depending on whether we have or have not applied the perturbation. If we Taylor expand an epsilon, we can show that this difference in expectation values becomes the expectation value of a commutator of operators. One of them is just x naught. That's like a poly x, right, on a single qubit. And one of them is this object, which might look a little bit scary. But this object is nothing more than the time evolution of an operator in the Heisenberg picture of quantum mechanics. So we can rewrite this expectation value as just the expectation value of this commutator of two operators, one of them evolved in time. Okay? This often goes by the name of linear response theory, but here I'm just sort of summarizing how it works. And as sort of one last mathematical bit of jargon, rather than writing out this expectation value every time, I'm just going to simplify things by putting these sort of double bars around the commutator. And that denotes something called the operator norm. You can just think of that as a way of saying, I want to know what is the largest possible matrix element of this commutator. Okay? So the upshot of this sort of little mathematical derivation, if you don't care about the equations, it's that this kind of combination of symbols encodes for us what is the maximal possible perturbation that I can cause, or sort of response I can cause at distance r after time t. Okay? And so what we're going to bound is sort of how much of an influence any perturbation at site 0 can have at site r. Okay? All right, any questions before we continue? Sure.
So that commutator, I could imagine that even if you wait a very short time, this commutator is non-zero, and I'll say, oh, I can perturb this side. But if the perturbation is somewhat far away, in a very small amount of time.
I will talk about this very shortly. Yes. It is not exact. It's true. This commutator is never necessarily exactly 0, but it can be extremely small. And that will be enough for many, many purposes. Yeah. This is just the definition of Heisenberg picture of quantum mechanics. Oh, it's possible. Oh, you mean here? Oh, yeah, OK.
XR is an operator someplace in the perturb this guy.
Yes. OK. All right. OK, so now, as Victor said, he's worried that this commutator is never 0. And that's indeed almost impossible unless t is equal to 0 exactly. But we'll see that nevertheless, this commutator can be extraordinarily small. Okay? So our goal is going to be to, with the little squiggle meaning not physics rigorous but not mathematically precise, our goal is to show that this commutator, which remember just tells us whether we can signal or not, is basically 0 if r is too big. So for any fixed time, if r is larger than some number v times t, we'd like to show that this commutator is basically 0. And if r is smaller than vt, we might not have any control over our bound, and we'll just say it's of order 1. Okay. The picture you should have in mind is that exactly like in special relativity, we're going to have sort of regime where when we haven't evolved for long enough, we can't cause any perturbation over here due to something here, whereas if we wait long enough, we can. Okay? And I'll call this a sort of Lieb-Robinson light cone with homage to relativity. OK. So I want to at least open up the hood a little bit and show you why you might expect a bound like this to work at all. And the first thing you might do when you want to show something like this is to Taylor expand for small times, okay? Because if we can't get this to work at small times, obviously it's not going to work at large times. So at small times, here's what happens. If we take the operator xr and Heisenberg evolve it in time, so you'll remember a few slides back, we had this formula. So I just Taylor expand in t, and I get this series of nested commutators with the Hamiltonian, okay? Now, at first glance, this might look kind of daunting because the Hamiltonian is something thermodynamically extensive. So if this thing sort of has a size that grows with the number of qubits, we would expect that this series is sort of pretty badly behaved, okay? However, the Hamiltonian is a very special kind of operator that acts on a large number of qubits. It's a sum of many terms, each of which only acts on a handful of qubits at a time. I think in the sort of toy example I showed earlier, we had either one body or two body terms. So if I look at this commutator of h with xr, if xr is a single site operator, that commutator will be a sum of terms that either acts on one or two sites, okay? Because if I have one operator acting over here and another one over here, they always commute through with each other, okay? So only an order 1 number of terms in this commutator don't identically vanish. In pictures, if I look at where my operator has support, I start off acting on site R, and then I move to an operator that acts either on one or two sites. I could also act here and one site to the right, but I got tired of drawing. OK, we can keep doing this again. At the next order, we can again kind of grow by one site. Sometimes we shrink by one site. That's also OK. But the point is that for this operator to fail to commute with an operator way over here at site 0, right, we have to go at least r steps in this Taylor series, because we can only move by one lattice site at a time. The first term in this series that hits site 0, therefore, will have a sort of coefficient that's like t to the r over r factorial. That's coming from Taylor expanding an exponential. And the prefactor of that term will be, some coupling in the Hamiltonian, let's call it j, raised to the rth power. And if I use Stirling's approximation for the factorial, so r factorial is roughly r to the r, I get this scaling. And notice that this scaling is indeed never exactly 0 the moment t is finite. This is a non-zero number. However, if the object in parentheses is smaller than 1, right, then when r is big, this is exponentially tiny. And really at fixed time, as r gets large, this falls off even faster than exponential. And for all practical purposes, this is 0. Okay? So that's great. The only problem is that this argument is actually wrong, at least as stated. It's not wrong that this is the strength of the sort of non-vanishing term in our commutator at order r. But the problem is that if you keep going in the Taylor series, you find that it doesn't converge. The reason it doesn't converge is sort of related to the fact that you can have phase transitions. So Taylor expanding, just exponentials of a Hamiltonian can be very dangerous. The number of terms at order n grows as n factorial. And this sort of ruins the factorial from the exponential. Okay? All right. So to fix this problem, there are many ways of doing this. One way that I like was in my student's undergrad thesis, which is to use the unitarity of quantum mechanics to give a kind of souped-up time-dependent perturbation theory, where what you do is as follows. At leading order in your perturbation theory, you sort of sum up all the terms in our Taylor series where you never act with a term in the Hamiltonian that grows your operator from site r to r minus 1. So your operator is sort of always on site r or to the right. And then at sort of first order in our time-dependent perturbation theory, we allow all the terms that hop one site to the left, but then stop there. And we just keep on going. What this trick is doing for us is it's basically saying that as our operator grows, part of the growth is just kind of like a rotation among operators of the same size and that act on the same qubits, but we're just rotating between like different combinations of identity or x, y, or z. And that doesn't that doesn't help us signal, doesn't grow our commutator norm. So we shouldn't count that when we try to derive a bound. And more formally, you can show that these sort of blue terms are all unitary conjugations, and they don't increase the maximal matrix elements of operators. So using the triangle inequality, you can bound the you can bound actually all of the terms in this sum, and you find that they are bounded by our factorial exactly. Okay? So our heuristic bound is actually exact if we use a kind of clever reorganization of quantum mechanics. Okay? All right. So to recap what we've done, we've shown that in local quantum many-body systems, this funny operator norm, or more physically, the sort of strength of any signal that I can cause, is bounded by this T over R to the R, which decays extremely fast, okay, outside of the light cone. This is often derived as just this exponential. This is actually a very loose inequality. Okay? And this derives for us this picture where if we cause a perturbation here and we ask whether we can see any signal from that perturbation outside of our emergent light cone, we find that the answer is effectively no. Whereas if we wait for a long enough time, we lie within our emergent light cone, and we can always send signals. Or we can, in principle, send signals. Okay? And there's one other consequence of this Lieb-Robinson bound that we've derived, which is very useful. It turns out that you can show that if this inequality holds for all choice of operators, which it does because I didn't need to assume anything about which operators I was talking about, you can show that this statement is equivalent to this one, that a time-evolving operator can basically be approximated within this light cone. Okay? So this is sort of an alternate perspective. Yes?
Is it right to think of this as a fuzzy line? Because,
it's a fuzzy line, but with any reasonable error tolerance, you can basically make it a sharp line. Like you could say that with accuracy epsilon, I want my manipulations to be correct. And now I just say x is vt plus log epsilon, and you can think of it as a sharp line again. You can transmit sort of, but what you can't do is transmit any sort of useful amount of information. So maybe you want to just send a single bit worth of information. And
so what defines you? So I know what information is.
One bit.
1 bit is useful.
Right. The reason is because if you don't send that, then what's going to happen is you'll get a very, very weakly entangled state. And if you want to do something with that, for example, maybe you wanted to measure that state. Well, with high probability, you're going to measure the state back into something unentangled. And so you can't do something useful until you have about 1 bit worth of information that you've transmitted. I'll talk a little more about sort of actually what it takes to do something useful shortly. Yeah. OK. All right. So that's sort of about as much detail as I want to go into sort of what's lying under the hood of any of these manipulations. Now I want to kind of give you a bird's eye view of a number of applications of, Adam. Yeah.
So is there an assumption actually about dimensionality in this group?
No.
So if I go to a very large dimensional, like spatial dimension, don't I have to consider a very large number of paths that take me between 2 points?
So things like spatial dimensionality can change the constant prefactor in VLR. But that's basically it. So the only thing you might worry about is if you have some abstract graph that's like so, it's infinite dimensional and further so non-locally connected that like there are hubs in the graph that connect to a finite fraction of bits. And then you just lose thermodynamic extensivity if you're not careful. And if you sort of restore thermodynamics, it turns out usually you restore V being finite.
Yeah, I guess I was wondering whether if you have still a nearest neighbor connected graph at a higher dimension, the higher order dimension Taylor expression have so many paths associated with them.
So the number of paths of length r, if let's say everyone has at most k neighbors, the number of paths of length r is at most k to the r. So that just rescales V. Yeah. Okay. All right. So now let me describe some applications of this locality bound. The first one might seem a bit natural. So I mentioned that one equivalent formulation of this theorem is that time-evolved operators can be efficiently approximated within their Lieb-Robinson light cone. So this suggests that it's easy to simulate quantum dynamics on classical computers, at least local expectation values, because we can just simulate expectation value of xr of t by truncating inside of our Lieb-Robinson light cone. And indeed, this is what you do if you want to get a provably accurate simulation of quantum dynamics. The complexity of this grows exponentially in the volume contained within the light cone. That's just the number of qubits that we can influence, and this gives us the size of Hilbert space dimension that we need to keep on our computer. Okay? It turns out that Lieb-Robinson bounds also constrain how hard it would be to replace your digital classical computer with a digital quantum computer, which we all know there are many of. Okay. But in all seriousness, someday we hope to have working quantum computers, and we might want to simulate, solid state physics on that quantum computer to generate, or high energy physics, to generate e to the IHT on a quantum computer. There are a few tricks. So since this is unitary, we can split it up into little blocks where t is some order 1 time. And for each block, there's a sort of beautiful algorithm from HH, K, and L here. And what you do is you can approximate continuous Hamiltonian time evolution with a lot of short gates. So in this kind of cartoon, you should think of a gate acting on qubits that sort of run from here to here on the lattice. And this algorithm has provable accuracy guarantees. And those accuracy guarantees come from the Lieb-Robinson bound. Okay? They basically tell us how efficiently we can sort of make this truncation of a larger Hamiltonian into sort of smaller pieces. This tells us the complexity of doing quantum digital simulations, and it is exponentially better than the classical case. Okay? All right. So now let me answer Jamie's question about what I mean by doing something useful. So suppose that I would like to start with a bunch of unentangled qubits, and after time evolution, I would like to evolve them into a bell pair between maybe the left and the right ends of my system. I don't care what happens to the rest of the qubits, but I just want a bell pair that's as big as possible, or as widely separated as possible. And I claim that this can only be done if the distance between those qubits is smaller than 2 times this Lieb-Robinson distance, Vt. There's a factor of 2 here because you could imagine that what you should do is sort of prepare entanglement in the middle of the 2 qubits, and then you send kind of 1 qubit down the chain in each direction. Okay? Now, how do we make this precise using our Lieb-Robinson bound? Well, it's actually just a 3-line proof. It's 3 lines because it's big font. Okay? But what you do is you basically say, OK, the bell pair has entanglement or connected correlations that are non-trivial between sites 0 and r. Okay? But by the Lieb-Robinson theorem, if time evolution is short time, then I can approximate x naught of t and xr of t by small operators that act only within the Lieb-Robinson light cone. If that approximation is true, then this operator is to good approximation a tensor product which has 0 connected correlation, and that's a contradiction. So I have to wait until the Lieb-Robinson light cone basically reaches the midpoint, and then this argument fails, and I can prepare entanglement. Okay? So if I want to prepare a Bell pair, which allows me to do useful quantum tasks, like teleportation, then I have to wait for the Lieb-Robinson light cone. Okay? All right. Lieb-Robinson bounds don't just constrain how hard it is to prepare entanglement. They also tell us that useful entanglement is protected under unitary dynamics. One example of useful entanglement, besides a Bell pair, is called the GHZ state, or a cat state. The GHZ state will be a superposition of n qubits all in down or in state 0, plus those same n qubits all up or in state 1. Okay? And this state is useful, at least as far as I can tell, for quantum metrology. Okay? It allows us to do sensing at what's called the Heisenberg limit. The way this works is that we want to learn the value of some unknown parameter omega in a Hamiltonian that sort of independently acts on every spin and is a sum, let's say, of Pauli z1 through zn. The way that we use the GHZ state to learn omega very efficiently is that we just time evolve this state. And I'm sure there are many more experts on this than I am in the audience. But we just time evolve this state, and we pick up a relative phase between the two halves of the GHZ state. And this phase grows linearly with n. So by measuring, it turns out, single site Pauli X operators and looking at the sort of overall sign of the outcomes, we can basically detect this phase. And if we do the experiment many times, we can detect this phase with an accuracy that falls off as 1 over n, the number of qubits. And what would we do if we just had n sort of unentangled qubits, or 1 qubit, but we do the experiment n extra times? Well, using classical probability, we would find 1 over square root n, just from the central limit theorem. Okay? So this 1 over n here is sort of an honest quantum advantage over sort of unentangled or decoherent classical measurements. And for some jargon reason that someone will have to explain to me afterwards, the 1 over square root n is called the quantum limit. It really, OK, anyway. But the real quantum limit is this Heisenberg 1 over n. OK. That's the ideal experiment. But in real systems, you might have perturbations, here denoted with v. And perturbations are really scary if you think about the state evolution that we described before. Because if we turn on just local perturbations v, they are catastrophic to the GHZ state itself. We can see this by thinking about just time-independent perturbation theory. If we apply a perturbation that acts on every site, and it has a very small amplitude even on every site, the sort of first-order correction to the wave function will be very big. It will grow with n. Okay? And this is because perturbations, like everything in life, are thermodynamically extensive. However, the denominator in time-dependent perturbation theory cares about the many-body gap, which is not extensive. Okay? This is called an orthogonality catastrophe. And as we sort of hinted at before, this is a consequence of the fact that states are extremely fragile in many-body systems. So realistic perturbations to many-body systems completely destroy eigenstates. Okay? So the GHZ state, which was a combination of eigenstates of our original Hamiltonian, this is why our sensing algorithm was so nice, the GHZ state will now be some superposition of exponentially many different eigenstates. We have no idea what superposition it is. And so you might think that these kinds of perturbations just destroy the usefulness of being able to sense with this GHZ state. On the other hand, since we've learned that it's hard to prepare entangled states via the Lieb-Robinson bounds, you might expect that the useful entanglement of GHZ sort of can't be taken away instantly either. Maybe we can't express our GHZ state nicely in terms of eigenstates of the true H, but somehow it should still have some entanglement structure that's usable for this Heisenberg limited sensing. And recently, my student Chow and I have proved that this is indeed the case. I won't tell you really how it works, but we've found a protocol that can achieve quantum sensing at the Heisenberg limit with adaptive single-site measurements on the time-evolved state. So if you can prepare this sort of very useful entangled state, you can evolve it in time, even with a very perturbed Hamiltonian. The perturbation can actually be strong compared to the signal that you're trying to measure. Okay? And what we showed is that with a polynomial complexity classical algorithm aiding you, you can basically update the measurement basis for each single qubit measurement that you make. And if you do this correctly, you can actually sort of salvage your Heisenberg limit up to an order 1 factor. Okay? So this tells us that, so locality basically tells us that sort of useful entanglement is both difficult to create and difficult to destroy. Okay. All right. One final application of these Lieb-Robinson bounds that I'd like to highlight is, I think, quite surprising. It turns out that Lieb-Robinson bounds, which are about dynamics, right? How long does it take to send signals in quantum systems? These bounds also constrain static properties of gapped many-body systems. By gapped here, I mean that my Hamiltonian has, even as the number of qubits gets large, a finite energy difference between the ground and first excited state. Okay? And what made Lieb-Robinson bounds sort of not obscure was that in 2006, well, 2 times 2 authors basically used the Lieb-Robinson bounds to prove that having a gap in your many-body Hamiltonian meant that, let's say, at least if you have a unique ground state, that ground state cannot have long-range correlations. Okay? And just to say in a few words how it works, the key idea is that time evolution of operators is a kind of spectral filter. If you look at matrix elements in the energy eigenbasis, time evolution is just a phase factor. And you can find functions that sort of project you, that project out matrix elements between eigenstates whose energies differ by more than, well, any number you want. When you have a finite energy gap, you kind of don't need to evolve for very long in time to project out the ground state, because you only need to project out matrix elements with an order 1 energy difference. On the other hand, time evolution for finite time grows local operators by, inside of a finite light cone. And so this is sort of the intuition for why these Lieb-Robinson bounds actually constrain the physics of gapped systems, even though this is not a question about dynamics at all. We're asking questions about static physics. One application of this that we've recently investigated is to solve in a sort of rigorous way a very old problem in high energy and condensed matter physics called the false vacuum decay. I think the easiest way to think of this is in a sort of ferromagnet. So this is a solid state application. I start with a Hamiltonian that describes a ferromagnet which has 2 degenerate ground states, one where most of the spins point up and the other where most of the spins point down. Okay? This degeneracy is fragile, though, because if I turn on a longitudinal magnetic field, I can immediately lift the degeneracy of the ground state. And not only is the degeneracy lifted, but once I turn on this perturbation epsilon, one of my original vacua is sort of gets an energy that's extensive, so epsilon times n, and it is pushed very deep into the energy spectrum of a many-body Hamiltonian. So there are exponentially many eigenstates that I expect have lower energy than this so-called false vacuum state. Okay? So you might think at first glance that this ferromagnet is sort of extremely vulnerable to tiny perturbations. On the other hand, there's maybe a more kind of semi-classical perspective that suggests that the false vacuum is very stable. Okay? And that argument goes like this. let me start in the false vacuum, which I'll assume is most of the spins pointing up. Okay, I take a single spin and I flip it down. So if the false vacuum is unstable, then flipping this single spin down into the true vacuum should be very favorable, and I should just sort of cascade this everywhere. However, if I just flip one spin down, I have to pay a price, right, because this is a ferromagnet, and the spins want to align. By flipping a single spin down, I've basically created an excitation which has an energy proportional to my gap, delta. I only gain a tiny energy, epsilon, from aligning the spin to the true vacuum. This delta E is not 0, so this process will not be resonant. In perturbation theory, we would naively just treat this at first order and be done with it. So if we ask, when do we find the first resonance? Well, the first resonance occurs at order delta over epsilon. And what I have to do is take this single downspin and sort of flip delta over epsilon of its neighbors to also be down. And then finally, I can get enough energy gain from being in the true vacuum to sort of offset the price of my domain walls. Okay? And the fact that this occurs only at high order in perturbation theory suggests that this takes a time which is non-perturbative in 1 over epsilon to occur. Okay? I think this calculation is sort of most famous in the high energy literature, where Sidney Coleman in the 1970s used path integral methods to calculate the lifetime of the false vacuum. You can sort of imagine our universe might not be the true vacuum of the standard model, and we're all going to die someday when the true vacuum arises. And Coleman said, oh, don't worry too much. The true vacuum will have to wait a non-perturbatively long time to find it. But, OK, quantum field theory is often not a mathematically rigorous subject, but this calculation is sort of even more awkward. And it's very unclear what is actually being calculated from a mathematician's perspective. And so one might like to sort of have a more rigorous understanding of what it means to have a false vacuum and what is slow in the false vacuum decay. I should also note that this problem is not inconsistent with what I just said about an orthogonality catastrophe, because here we're not talking about eigenstates. Okay? We're talking about sort of local physics. Exact eigenstates may indeed be drastically different the moment I turn on this perturbation. Okay. So just to sort of summarize some of our recent work, what we've shown is that if you give me a many-body Hamiltonian with a gap, and I add local perturbations of small strength epsilon, we can find a unitary U, which is sort of like time evolution for time epsilon with something quasi-local. And this unitary rotation basically takes this perturbed Hamiltonian, and it rotates it into something which is block diagonal between ground and excited states of H0, plus non-perturbatively small perturbations. First, we can now give a rigorous definition of the false vacuum. The false vacuum is simply the state of H star, which is sort of in the ground state subspace, at least as measured by H0, but which has high energy. So this is a very rigorous notion of what a false vacuum is. And it makes sense even beyond perturbation theory within QFT. What does it mean that the false vacuum has a long lifetime? Again, this is not a statement about any eigenstates. It's a statement about local observables. And what this transformation shows you is that by the Lieb-Robinson theorems, local time evolution for a small time epsilon doesn't do very much to operators. So if we look at correlation functions, we can go to this kind of idealized basis, and we see that local correlations are hardly disturbed, except in this new basis, the perturbation is sort of extremely weak. So the false vacuum protection is really sort of that local correlation functions are only sensitive at very long time scales to our perturbation. Yes? Yes, yes, yes. So this perturbation, it's e to the minus delta over epsilon. So if delta is 0, this doesn't work. Yeah. Yeah. OK. Right. OK, so for the last 10 minutes or so, I'd like to describe a little bit about sort of new notions of locality that we've derived, and if you like, sort of which systems are local and which systems are not. OK. The Lieb-Robinson bounds that we described are for sort of systems with nearest neighbor interactions. But basically, no systems in nature have nearest neighbor interactions. Okay? Most systems in nature have power law interactions, all of which kind of come from the fact that things are charged, right? But we have Coulomb interactions that are 1 over r. Van der Waals interactions are 1 over r to the 6. And we might ask, which of these power law interactions, if any, kind of break the Lieb-Robinson bounds? Can we send signals as fast as we want if we have Coulomb interacting particles? Or what about Van der Waals interacting things? So we'll sort of generally study this problem by thinking about Hamiltonians that couple qubits I and j with a strength that decays as 1 over the distance between I and j to some power alpha. And if alpha goes to infinity, we should expect that we get the Lieb-Robinson light cone back, because that's just like nearest neighbor interactions. If alpha equals 0, there's really no spatial locality left, so we shouldn't have a light cone. And the question is sort of, if alpha is finite, do we ever get this? Do we get something more like the purple line? Kind of what happens? So this problem has been studied a lot for the past 20 years. And OK, in 2000, we had this kind of logarithmic light cone, which is pretty crap. Sorry, Hastings and Coma. Then Alexei Gorshkov and friends did a lot better in 2015. So this bound, what they showed is basically that when alpha becomes very large, you can get something that looks kind of almost linear, but they ultimately couldn't show that the Lieb-Robinson velocity was strictly finite. Okay? And so in 2019, my student and I first proved that in 1 dimension, when alpha is larger than 3, so dipole-dipole interactions basically are our cutoff. For alpha larger than 3, we proved that signals can only be sent with a finite velocity. And shortly after that, Kuwahara and Saito generalized our result to all dimensions, and these papers kind of improve various aspects. The punchline is that when this power law decay is larger than 2d plus 1, you can't send signals any better than if you had local interactions, any faster. If alpha is 2d, you can send signals so fast that it's almost as good as having all-to-all interactions. Okay. It's not quite that good, but it's pretty close. Okay. And then, in between, there's some algebraic decay. Okay. What I think is kind of shocking about this is that Van der Waals interactions, which are usually approximated as just nearest neighbor because they fall off pretty quickly, actually in the asymptotic limit are so non-local that they allow you to prepare useful entangled states in nearly finite time, or in nearly constant time, even as the number of qubits grows very large. Okay. Let me give you a sort of brief cartoon for why power law interactions are this useful. So suppose that I give you 2 GHZ states, one on a sort of bunch of qubits I'll call left, and one on qubits that I'll call right. And I have these power law interactions right between any qubit in the left and any qubit in the right. I can use a special Hamiltonian to take this state and prepare this one, where the 1-1 sort of piece of the wave function just gets a minus sign. This is what would generate what are called control Z gates. The rate at which I can accumulate phase, I can sort of count. It's the number of interactions that I have, which is the number of sites in the left times the number of sites in the right, times the strength of the terms in the Hamiltonian. If these balls have size r, I have r to the d terms in each ball in d spatial dimensions. the interaction dies off as r to the minus alpha, and so the rate at which I can accumulate phase is r to the 2d minus alpha. And this explains why we see the sort of exponents that we do when we look at Lieb-Robinson bounds. Okay. All right. Another generalization that we've looked at is to Bose gases. So experiments also can have bosonic degrees of freedom. And here there's sort of a scarier infinity. For one thing, not only is the Hilbert space uncountable, but on any given lattice site, we already have a sort of infinite Hilbert space. We can put as many bosons as we want on a single site. And this is scary because physical Hamiltonians are actually unbounded. So here's a sort of classic Hamiltonian describing a Bose-Hubbard model. Okay? And in this Hamiltonian, these operators B and B dagger are just the standard harmonic oscillator operators. And these operators are unbounded. If I act with B dagger on a state that has n bosons, I get this square root n plus 1. Okay? And this, you might worry, kind of ruins any notions of locality with bosonic models, because you could imagine piling up all the bosons at one place, and then all of these operators, right, become increasingly large. And so you might think that you can send signals really fast by piling up all of your particles. We were able to prove 2 years ago that that cannot happen, at least in one dimension. So if you have a finite boson density, we were able to prove that the Lieb-Robinson theorem basically generalizes with a density-dependent velocity. Okay? And our proof uses kind of creative techniques coming from classical probability theory, which I won't explain. It turns out that in higher dimensions, this pile-up problem actually happens in principle. So in higher dimensions, bosonic systems really can send signals arbitrarily fast. But in one dimension, you do have a kind of light cone, just as in spin models. OK. The last extension we've looked at is to dynamics with measurement. And here there's a sort of old paradox from Einstein, Podolsky, and Rosen, who worried about the following issue. Let's take the same Bell pair we talked about before, and suppose that someone at site 0 measures their qubit. By measuring the wave function, it collapses, and no matter how far away the other qubit is, right, the wave function has sort of instantly collapsed, and naively something very non-local has happened. And so Einstein et al. Were very worried that this allowed you to send signals, and this could violate relativity. The relativity problem is sort of easy to resolve. The two observers that are making measurements can't check that their measurements agree until after they send a classical signal that propagates at the speed of light. But this raises another question, which is, does actual quantum information get transmitted in this classical signal? Okay? And this is important because measurement is something we can build into a future quantum computer. So if we can use measurement to beat the Lieb-Robinson bound, then this actually will help us, prepare entangled states and do useful operations. OK. Unfortunately, it turns out that measurements cannot be used to just beat the Lieb-Robinson bound, at least not without cost. So it turns out that if you're willing, for each qubit worth of information that you want to send, if you're willing to sort of make m measurements, you can increase the velocity at which signals are sent by this factor 2m plus 1. And the sort of cartoony picture for this is that you need to join up Lieb-Robinson light cones between everything that you measure and the operator you're trying to send. Okay? And for those of you in the know, what this means is that quantum repeater networks are the optimal way to send signals in a quantum computer. Okay? And if you want to prepare an entangled Bell pair, let's say in finite time, you have to use an extensive number of qubits in the middle that are going to be sort of wasted to send this one signal faster. To prove this result, we use a beautiful formulation of measurement due to Stein spring, in which the measurement process itself is unitary. So for every measurement that you're going to make, you append an extra qubit to the Hilbert space that's going to store the outcome of the measurement. And what the measurement does is it just entangles the measurement outcome with the physical state. Okay? This is sort of like the many worlds formalism, but I'm not a philosopher, and I may be a kind of anti-philosopher. I just want something that works. And this formalism allows us to understand how measurements work, so it's nice. Okay? Because this is mathematically unitary, we can now talk about a Heisenberg picture for operator dynamics. And this is sort of how we prove these bounds on dynamics with measurement. In a nutshell, the way they work is that in the Heisenberg picture, you kind of read time evolution backwards. So if physical states are prepared by first entangling qubits, measuring some of them, and then doing quantum error correction, on operators you go the other way. So you use knowledge to create entanglement between sort of knowledge outcomes and physical qubits, and then you entangle physical qubits. And OK, I'm sure this is too fast, but this is kind of, in 60 seconds, how we can understand dynamics with measurement in a new way. OK, so just to sort of wrap things up, the way we think about physics is fundamentally organized around locality. Theories of relativity, effective field theory are all based around locality. And the Lieb-Robinson theorem tells us what locality implies about quantum dynamics, and it gives us emergent speed limits on information. And these have both fundamental and practical implications, and I think there are many interesting future questions. I have money, so I kind of need to think about this for a little longer. Thank you.
I want to be respectful of people's time. We're running a little bit long, but maybe we could take just one or two very quick questions, and then if people have more questions afterwards, they